Man, it's crazy how long I can read. I cannot believe this. Like a few months ago when I first started doing some of this reading practice, I would get maybe an hour, 2 hours in, and I was just dead. My eyes are so tired. My body just wanted to go be done. And now it's like I can seriously just sit down and do this forever. All right, so go ahead and yellow this guy. And I am going to go ahead and do one more OpenStax. I'd like to go ahead and just finish that whole day on yellow. So I'm going to go to the next book. So I'm going to go ahead and let's see. Oops. There we go. Insert one column left. And I'm going to go ahead and just do this. One, and then add in. So what this does is this keeps track of which chapters I've read. Or not, maybe not which chapters, but how many I've read. So I've read one chapter biology, so I got 46 to go. Okay. Yeah, cool. I'm going to go ahead and increase one to the right. And I'll put the workouts, W for the workout there. So, cool. You know what? I'm going to do one more. Because why not? There we go. One left. And so I did this one yesterday. No. Yeah, yesterday was biology. So that was 9, 29, 20, 23. And then this one, 9, 30. This way I can keep track of when I do it. Or when I last updated it. So when the number here changes, the date will change. Because I also have it written here. So that's basically what the Bible's been doing. It's constantly going back and forth. So sociology, OpenStax, sociology 1. All right, so next is astronomy. So let's go ahead and back out of that. Back out of that. That's going to be economies, or sorry, that's going to be down here. Astronomy 2E. And then download PDF. Go to File. I think I'm recording. Yeah, I am. All right. Astronomy 2E. Let's get straight to chapter 1. And let's zoom in twice. 3 times. There you go. All right. Chapter 1 of the astronomy book. Science and the Universe, a brief tour. Chapter outline. 1.1, the nature of astronomy. 1.2, the nature of science. 1.3, the laws of nature. 1.4, numbers in astronomy. 1.5, consequences of light travel time. 1.6, a tour of the universe. 1.7, the universe on the large scale. 1.8, the universe of the very small scale. 1.9, a conclusion and a beginning. Introduction. We invite you to come along a series of voyages to explore the universe as astronomers understand it today. Beyond Earth are vast and magnificent realms full of objects that have no counterpart on our home planet. Nevertheless, we hope to show you that the evolution of the universe has been directly responsible for your presence on Earth today. Along your journey, you will encounter a canyon system so large on Earth it would stretch from Los Angeles to Washington, D.C., a crater and other evidence on Earth that tell us that the dinosaurs died because of a cosmic collision, A tiny moon whose gravity is so weak that one good throw from its surface could put a baseball into orbit. A collapsed star so dense that to duplicate its interior, we would have to squeeze every human being on Earth into a single raindrop. Exploding stars whose violent end could wipe clean all the life forms on a planet orbiting a neighborhood star. A cannibal galaxy that has already consumed a number of its smaller galaxy neighbors and is not yet finished finding new victims. A radio echo that is faint but unmistakable signal of the creation event for our universe. Such discoveries are what make astronomy such an exciting field for scientists and many others, but you will explore much more than just the objects in our universe and the latest discoveries about them. We will pay equal attention to the process by which we have come to understand the realms beyond Earth and the tools we use to increase that understanding. We gather information about the cosmos from the messages the universe sends our way. Because the stars are the fundamental building blocks of the universe, decoding the messages of starlight has been a central challenge and triumph of modern astronomy. By the time you have finished reading this text, you will know a bit about how to read that message and how to understand what it is telling us. 1.1 The nature of astronomy. Astronomy is defined as the study of objects that lie beyond our planet, Earth, and the processes by which these objects interact with one another. We will see, though, that it is much more. It is also humanity's attempt to organize what we learn into a clear history of the universe, from the instant of its birth in the Big Bang to the present moment. Throughout this book, we emphasize that science is a progress report, one that changes constantly as new techniques and instruments allow us to probe the universe more deeply. In considering the history of the universe, we will see again and again that the cosmos evolves, it changes in profound ways over long periods of time. For example, the universe made of carbon, the calcium, and the oxygen necessary to construct something as interesting and complicated as you. Today, many billions of years later, the universe has evolved into a more hospitable place for life. Tracing the evolutionary processes that continue to shape the universe is one of the most important parts of modern astronomy. 1.2 The nature of science. The ultimate judge in science is always what nature itself reveals based on observation, experiments, models, and testing. Science is not merely a body of knowledge, but a method by which we attempt to understand nature and how it behaves. This method begins with many observations over a period of time. From the trends found through observations, scientists can model the particular phenomena we want to understand. Such models are always approximations of nature, subject to further testing. As a concrete astronomical example, ancient astronomers constructed a model that Earth was the center of the universe and everything moved around it in circular orbits. At first, our available observations of the sun, moon, and planets did fit this model. However, after further observations, the model had to be updated by adding circle after circle to represent the movements of the planets and around the Earth at the center. As the centuries passed and improved, instruments were developed for keeping track of objects in the sky. The old model could no longer explain all the observed facts. As we will see in the chapter on observing the sky, the birth of astronomy, a new model with the sun at the center fit the experimental evidence better. After a period of philosophical struggle, it became accepted as our view of the universe. When they are first proposed, new models or ideas are sometimes called hypotheses. You may think there can be no new hypotheses in a science such as astronomy, that everything important has already been learned. Nothing could be further from the truth. Throughout this textbook, you will find discussions of recent and occasionally still controversial hypotheses in astronomy. For example, the significance that the huge chunks of rock and ice that hit the Earth have for life on Earth itself is still debated. And while the evidence is strong that vast quantities of invisible dark energy make up the bulk of the universe, scientists have no convincing explanation for what the dark energy actually is. Resolving these issues will require difficult observations done at the forefront of our technology, and all such hypotheses need further testing before we incorporate them fully into our standard astronomical models. This last point is crucial. A hypothesis must be a proposed explanation that can be tested. The most straightforward approach to such testing in science is to perform an experiment. If the experiment is conducted properly, its results either will agree with the predictions of the hypothesis or they will contradict it. If the experimental results is truly inconsistent with the hypothesis, a scientist must discard the hypothesis and try to develop an alternative. If the experimental result agrees with predictions, this does not necessarily prove that the hypothesis is absolutely correct. Perhaps later experiments will contradict crucial parts of the hypothesis. But the more experiments that agree with the hypothesis, the more likely we are to accept the hypothesis as a useful description of nature. One way to think about this is to consider a scientist who is born and lives on an island where only black sheep live. Day after day, the scientist encounters black sheep only, so he or she hypothesizes that all sheep are black. Although every observed sheep adds confidence to the hypothesis, the scientist only has to visit the mainland and observe one white sheep to prove the hypothesis wrong. When you read about experiments, you probably have a mental picture of a scientist in a laboratory conducting tests or taking careful measurements. This is certainly the case for a biologist or a chemist. But what can astronomers do when our laboratory is the universe? It's impossible to put a group of stars into a test tube or to order another comet from a scientific supply company. As a result, astronomy is sometimes called an observational science. We often make our tests by observing many samples of the kind of object we want to study and noting carefully how different samples vary. New instruments and technology can let us look at astronomical objects from new perspectives and in greater detail. Our hypotheses are then judged in the light of this new information, and they pass or fail in the same way we would evaluate the result of a laboratory experiment. Much of astronomy is also a historical science, meaning that what we observe has already happened in the universe, and we can do nothing to change it. In the same way, a geologist cannot alter what has happened to our planet, and a paleontologist cannot bring an ancient animal back to life. While this can make astronomy challenging, it also gives us fascinating opportunities to discover the secrets of our cosmic past. You might compare an astronomer to a detective trying to solve a crime that occurred before the detective arrived at the scene. There is lots of evidence, but both the detective and the scientist must sift through and organize the evidence to test various hypotheses about what actually happened. And there is another way in which the scientist is like a detective. They both must prove their case. The detective must convince the district attorney, the judge, and perhaps ultimately the jury that his hypothesis is correct. Similarly, the scientist must convince colleagues, editors of journals, and ultimately a broad cross section of other scientists that her hypothesis is provisionally correct. In both cases, one can only ask for evidence beyond a reasonable doubt. And sometimes new evidence will force both the detective and the scientist to revise their last hypotheses. This self-correcting aspect of science sets it off from most human activities. Scientists spend a great deal of time questioning and challenging one another, which is why applications for project funding, as well as reports for publication in academic journals, go through an extensive process of peer review, which is a careful examination by other scientists in the same field. In science, everyone is encouraged to improve upon experiments and to challenge any and all hypotheses. New scientists know that one of the best ways to advance their careers is to find a weakness in our current understanding of something and to correct it with a new or modified hypothesis. This is one of the reasons science has made such dramatic progress. An undergraduate science major today knows more about science and math than Sir Isaac Newton, one of the most renowned scientists who ever lived. Even in this introductory astronomy course, you will learn about objects and processes that no one a few generations ago even dreamed existed. 1.3 The Laws of Nature. Over centuries, scientists have extracted various scientific laws from countless observations, hypotheses, and experiments. These scientific laws are, in a sense, the rules of the game that nature plays. One remarkable discovery about nature, one that underlies everything you will read about in this text, is that the same laws apply everywhere in the universe. The rules that determine the motion of the stars are so far away that your eye cannot see them, are the same laws that determine the arc of a baseball after a batter has hit it out of the park. Note that without the existence of such universal laws, we could not make much headway in astronomy. If each pocket of the universe had different rules, we would have little chance of interpreting what happened in other neighborhoods. But the consistency of the laws of nature gives us enormous power to understand distant objects without traveling to them and learning the local laws. In the same way, every region of a country had completely different laws. It would be very difficult to carry out commerce or even to understand the behavior of people in those different regions. A consistent set of laws, though, allows us to apply what we learn or practice in one state to any other state. This is not to say that our current scientific models and laws cannot change. New experiments and observations can lead to new, more sophisticated models, models that can include new phenomena and laws about their behavior. The general theory of relativity proposed by Albert Einstein is a perfect example of such a transformation that took place about a century ago. It led us to predict and eventually to observe a strange new class of objects that astronomers call black holes. Only the patient process of observing nature ever more carefully and precisely can demonstrate the validity of such new scientific models. One important problem in describing scientific models has to do with the limitations of language. When we try to describe complex phenomena in everyday terms, the words themselves may not be adequate to do the job. For example, you may have heard the structure of an atom likened to a miniature solar system. While some aspects of our modern model of the atom do remind us of planetary orbits, many other of its aspects are fundamentally different. This problem is the reason scientists often prefer to describe their models using equations rather than words. In this book, which is designed to introduce the field of astronomy, we use mainly words to discuss what scientists have learned. We avoid complex math, but if this course piques your interest and you go on in science, more and more of your studies will involve the precise language of mathematics. 1.4 Numbers in Astronomy. In astronomy, we deal with distances on a scale you may never have thought about before, with numbers larger than any you may have encountered. We adopt two approaches that make dealing with astronomical numbers a little bit easier. First, we use a system for writing large and small numbers called scientific notation. This system is very appealing because it eliminates the many zeros that can seem overwhelming to the reader. In scientific notation, you want to write a number such as 500 million. You express it as 5 times 10 to the 8th power. The small raised number after the 10, called the exponent, keeps track of the number of places we have to move the decimal point to the left to convert 500 million to 5. If you are encountering this system for the first time or would like a refresher, there's this Appendix C has all that information. The second way we try to keep numbers simple is to use a consistent set of units. The Metric International System of Units, or SI. The metric system is summarized in Appendix D. A common unit astronomers use to describe distances in the universe is a light year, which is the distance light travels during 1 year. Because light always travels at the same speed, and because its speed turns out to be the fastest possible speed in the universe, it makes a good standard for keeping track of distances. You might be confused because a light year seems to imply that we are measuring time, but this mix-up of time and distance is common in everyday life as well. For example, when your friend asks where the movie theater is located, you might say about 20 minutes from downtown. So how many kilometers are there in a light year? Light travels at the amazing pace of 3 times 10 to the 5 kilometers per second, which makes a light year 9.46 times 10 to the 12 kilometers. You might think that such a large unit would reach the nearest star easily, but the stars are far more remote than our imaginations might lead us to believe. Even the nearest star is 4.3 light years away, more than 40 trillion kilometers. Other stars visible to the unaided eye are hundreds to thousands of light years away. 1.5 Consequences of light travel time. There's another reason the speed of light is such a natural unit of distance for astronomers. Information about the universe comes to us almost exclusively through various forms of light, and all such light travels at the speed of light, that is, 1 light year every year. This sets a limit on how quickly we can learn about events in the universe. If a star is 100 light years away, the light we see from it tonight left that star 100 years ago and is just now arriving in our neighborhood. The soonest we can learn about any changes in that star is 100 years after the fact. For a star 500 light years away, the light we detect tonight left 500 years ago and is carrying 500-year-old news. Because many of us are accustomed to instant news from the internet, some might find this frustrating. You mean when I see that star up there, you ask, I won't know what's actually happening there for another 500 years? But this isn't the most helpful way to think about the situation. For astronomers, now is when the light reaches us here on Earth. There is no way for us to know anything about that star until its light reaches us. But what at first may seem a great confusion is actually a tremendous benefit in disguise. If astronomers really want to piece together what has happened in the universe since its beginning, they must find evidence about each epoch of the past. Where can we find evidence today about cosmic events that occurred billions of years ago? The delay in the arrival of light provides an answer to this question. The farther out in space we look, the longer the light has taken to get here, and the longer ago it left its place of origin. By looking billions of light years out into space, astronomers are actually seeing billions of years into the past. In this way, we can construct the history of the cosmos and get a sense of how it has evolved over time. This is one reason why astronomers strive to build telescopes that can collect more and more of the faint light of the universe. The more light we collect, the fainter the objects we can observe. On average, fainter objects are farther away and can therefore tell us about periods of time even deeper in the past. Instruments such as the Hubble Space Telescope and the Very Large Telescope in Chile are giving astronomers views of deep space and deep time better than any we have had before. 1.6 A Tour of the Universe. We can now take a brief introductory tour of the universe as astronomers understand it today to get acquainted with the types of objects and distances you will encounter throughout the text. We begin at home with Earth, a nearly spherical planet about 13,000 kilometers in diameter. A space traveler entering our planetary system would easily distinguish Earth from the other planets in our solar system by the large amount of liquid water that covers some 2/3 of its crust. If the traveler had equipment to receive radio or television signals, or came close enough to see the lights of our cities at night, she would soon find signs that this watery planet has sentient life. Our nearest astronomical neighbor is Earth's satellite, commonly called the Moon. Uh, Notice how small we have to make these bodies to fit them on the diagram. So they made a little figure, so figure 1.7. I wasn't going to read that. So figure 1.7 shows Earth and the Moon drawn to scale on the same diagram. Notice how small we have to make the bodies to fit them on the page with the right scale. The Moon's distance from Earth is about 30 times Earth's diameter, or approximately 384,000 kilometers. And it takes about a month for the Moon to revolve around Earth. The Moon's diameter is 3,476 kilometers, about 1/4 the size of Earth. Light takes 1.3 seconds to travel between Earth and the Moon. If you've seen videos of the Apollo flights to the Moon, you may recall that there was a delay of about 3 seconds between the time mission control asked a question and the time the astronauts responded. This was not because the astronauts were thinking slowly, but rather because it took the radio waves almost 3 seconds to make the round trip. Earth revolves around our star, the Sun, which is about 150 million kilometers away, approximately 400 times as far away from us as the Moon. We call the average Earth-Sun distance an astronomical unit because in the early days of astronomy, it was the most important measuring standard. Light takes slightly more than 8 minutes to travel 1 astronomical unit, which means the latest news we receive from the Sun is always 8 minutes old. The diameter of the Sun is about 1.5 million kilometers. Earth could fit comfortably inside one of the minor eruptions that occurs on the surface of our star. If the Sun were reduced to the size of a basketball, Earth would be a small apple seed about 30 meters from the ball. It takes Earth 1 year to go around the Sun at our distance. To make it around, we must travel at approximately 110,000 kilometers per hour. If you like, I'm not reading the parentheses. Because gravity holds us firmly to Earth, and there is no resistance to Earth's motion in the vacuum of space, we participate in this extremely fast-moving trip without being aware of it day to day. Earth is only one of 8 planets that revolve around the Sun. These planets, along with their moons and swarms of other smaller bodies, such as dwarf planets, make up the solar system. A planet is defined as a body of significant size that orbits a star and does not produce its own light. Later in the book, this definition will be modified a bit, but it is perfectly fine for now as you begin your voyage. We are able to see the nearby planets in our skies only because they reflect the light of our local star, the Sun. If the planets were much further away, the tiny amount of light they reflect would usually not be visible to us. The planets we have so far discovered orbiting other stars were found from the pull of their gravity exerts on their parent stars, or from the light they block from their stars when they pass directly in front of them. We can't see most of these planets directly, although a few are now being imaged directly. The Sun is our local star, and all the other stars are also enormous balls of glowing gas that generate vast amounts of energy by nuclear reactions deep within. We will discuss the processes that cause stars to shine in much more detail later in the book. The other stars look faint only because they are so very far away. If we continue our basketball analogy, Proxima Centauri, the nearest star beyond the Sun, which is 4.3 light years away, would be almost 7,000 kilometers from the basketball. When you look up at a star-filled sky on a clear night, All the stars visible to the unaided eye are part of a single collection of stars we call the Milky Way galaxy, or simply the galaxy. The sun is one of hundreds of billions of stars that make up the galaxy. Its extent, as we will see, staggers the human imagination. Within a sphere 10 light years in radius centered on the sun, we find roughly 10 stars. Within a sphere 100 light years in radius, there are roughly 10,000 stars. Far too many to count or name, but we have still traversed only a tiny part of the Milky Way galaxy. Within a 1,000 light year sphere, we find some 10 million stars. Within a sphere of 100,000 light years, we finally encompass the entire Milky Way galaxy. Our galaxy looks like a giant disk with a small ball in the middle. If we could move outside our galaxy and look down on the disk of the Milky Way from above, it would probably resemble the galaxy in figure 1.9 with its spiral structure outlined by the blue light of hot adolescent stars. The sun is somewhat less than 30,000 light years from the center of the galaxy, in a location with nothing much to distinguish it. From our position inside the Milky Way galaxy, we cannot see through to its far rim because the space between the stars is not completely empty. It contains a sparse distribution of gas intermixed with tiny solid particles that we call interstellar dust. This gas and dust collect into enormous clouds in many places in the galaxy, becoming the raw material for future generations of stars. Figure 1.10 shows an image of the disk of the galaxy as shown from our vantage point. That's crazy. Typically, the interstellar material is so extremely sparse that the space between the stars is a much better vacuum than anything we can produce in terrestrial laboratories. Yet the dust in space, building up over thousands of light years, can block the light of more distant stars, like the distant buildings that appear from our view on a smoggy day in Los Angeles. The more distant regions of the Milky Way galaxy cannot be seen behind the layers of interstellar smog. Luckily, astronomers have found that stars and raw materials shine with various forms of light, some of which do penetrate the smog, and so we have been able to develop a pretty good map of the galaxy. Recent observations, however, have also revealed a rather surprising and disturbing fact. There appears to be much more to the galaxy than meets the eye. From various investigations, we have evidence that much of our galaxy is made of material we cannot currently observe directly with our instruments. We therefore call this component of the galaxy dark matter. We know that dark matter is there by the pull of its gravity exerts on the stars and raw material we can observe, but what this dark matter is made of and how much of it exists remain a mystery. Furthermore, this dark matter is not confined to our galaxy. It appears to be an important part of other star groupings as well. By the way, not all stars live by themselves, as the sun does. Many are born in double or triple systems with 2, 3, or more stars revolving about each other. Because the stars influence each other in such close systems, multiple stars allow us to measure characteristics that we cannot discern from observing single stars. In a number of places, enough stars have formed together that we recognize them as star clusters. Some of the largest star clusters that astronomers have cataloged contain hundreds of thousands of stars and take up volumes of space hundreds of light years across. You may hear stars referred to as eternal, but in fact, no star can last forever. Since the business of stars is making energy, and energy production requires some sort of fuel to be used up, eventually all stars run out of fuel. This news should not cause you to panic, though, because our sun still has at least 5 or 6 billion years to go. Ultimately, the sun and all stars will die, and it is in their death throes that some of the most intriguing and important processes of the universe are revealed. For example, we now know that many of the atoms in our bodies were once inside stars. These stars exploded at the ends of their lives, recycling their material back into the reservoir of the galaxy. In this sense, all of us are literally made of recycled stardust. 1.7. The universe on the large scale. In a very rough sense, you can think of the solar system as your house or apartment and the galaxy as your town made up of many houses and buildings. In the 20th century, astronomers were able to show that just as our world is made up of many, many towns, so the universe is made up of enormous numbers of galaxies. Galaxies stretch as far into space as our telescopes can see, many billions of them within the reach of modern instruments. When they were first discovered, some astronomers called galaxies island universes, and the term is aptly descriptive. Galaxies do look like islands of stars in the vast dark seas of intergalactic space. The nearest galaxy discovered in 1993 is a small one that lies 70,000 light years from the sun in the direction of the constellation Sagittarius, where the smog in our own galaxy makes it especially difficult to discern. Beyond the Sagittarius dwarf galaxy lie two other small galaxies, about 160,000 light years away. First recorded by Magellan's crew as he sailed around the world, these are called the Magellanic Clouds. All three of these small galaxies are satellites of the Milky Way galaxy, interacting with it through the force of gravity. Ultimately, all three may even be swallowed by our much larger galaxy, as other small galaxies have been over the course of cosmic time. The nearest large galaxy is a spiral quite similar to our own, located in the constellation of Andromeda, and is called the Andromeda Galaxy. It is also known by one of its catalog numbers, M31. M31 is a little more than 2 million light years away, along with the Milky Way, is part of a small cluster of more than 50 galaxies referred to as the Local Group. At distances of 10 to 15 million light years, we find other small galaxies, galaxy groups, and then at about 50 million light years, there are more impressive systems with thousands of member galaxies. We have discovered that galaxies occur mostly in clusters, both large and small. Some of the clusters themselves form into larger groups called superclusters. The Local Group is part of a supercluster of galaxies called the Virgo supercluster, which stretches over a diameter of 110 million light years. We are just beginning to explore the structure of the universe at these enormous scales and are already encountering some unexpected findings. At even greater distances, where many ordinary galaxies are too dim to see, we find quasars. These are brilliant centers of galaxies, glowing with the light of an extraordinary energetic process. The enormous energy of the quasars is produced by gas that is heated to a temperature of millions of degrees as it falls toward a massive black hole and swirls around it. The brilliance of quasars makes them the most distant beacons we can see in the dark oceans of space. They allow us to probe the universe 10 billion light years away or more, and thus 10 billion years or more in the past. With quasars, we can see way back close to the Big Bang explosion that marks the beginning of time. Beyond the quasars and the most distant visible galaxies, we have detected the feeble glow of the explosion itself, filling the universe and thus coming to us from all directions in space. The discovery of this afterglow of creation is considered to be one of the most significant events in 20th century science, and we are still exploring the many things it has to tell us about the earliest times of the universe. Measurements of the properties of galaxies and quasars in remote locations require large telescopes, sophisticated light amplifying devices, and painstaking labor. Every clear night at observatories around the world, astronomers and students are at work on such mysteries as the birth of new stars and the large-scale structure of the universe, fitting their results into the tapestry of our understanding. The universe of the very small. The foregoing discussion has likely impressed on you that the universe is extraordinarily large and extraordinarily empty. And on average, it is 10,000 times more empty than our galaxy. Yet, as we have seen, even the galaxy is mostly empty space. The air we breathe has about 10 to the 19 atoms in each cubic centimeter, and we usually think of air as empty space. In the interstellar gas of the galaxy, there is about one atom in every cubic centimeter. Intergalactic space is filled so sparsely that to find one atom on average, we must search through a cubic meter of space. Most of the universe is fantastically empty. Places that are dense, such as the human body, are tremendously rare. Even our most familiar solids are mostly space. If we could take apart such a solid piece by piece, we would eventually reach the tiny molecules from which it is formed. Molecules are the smallest particles into which any matter can be divided while still retaining its chemical properties. A molecule of water, for example, consists of two hydrogen atoms and one oxygen atom bonded together. Molecules, in turn, are built of atoms, which are the smallest particles of an element that can still be identified as that element. For example, an atom of gold is the smallest possible piece of gold. Nearly 100 different kinds of atoms exist in nature. Most of them are rare, and only a handful account for more than 99% of everything which we come in contact. The most abundant elements in the cosmos today are listed in Table 1.1. Think of this table as the greatest hits of the universe when it comes to the elements. Note that the list includes the four elements most common in life on Earth: hydrogen, carbon, nitrogen, and oxygen. All atoms consist of a central positively charged nucleus surrounded by negatively charged electrons. The bulk of matter in each atom is found in the nucleus, which consists of positive protons and electrically neutral neutrons, all bound tightly together in a very small space. Each element is defined by the number of protons in its atom. Thus, any atom with 6 protons in its nucleus is called carbon, any with 50 protons is called tin, and any with 70 protons is called ytterbium. The distance from an atomic nucleus to its electrons is typically 100,000 times the size of the nucleus itself. This is why we say that even solid matter is mostly space. A typical atom is far emptier than the solar system out to Neptune. This is one reason atoms are not like miniature solar systems. Remarkably, physicists have discovered that everything that happens in the universe, from the smallest atomic nucleus to the largest superclusters of galaxies, can be explained through the action of only 4 forces: gravity, electromagnetism, and 2 forces that act at the nuclear level. The fact that there are 4 forces has puzzled physicists and astronomers for many years and has led to a quest for a unified picture of nature. 1.9 A conclusion and a beginning. If you are new to astronomy, you have probably reached the end of our brief tour in this chapter with mixed emotions. On the one hand, you may be fascinated by some of the new ideas you've read about, and you may be eager to learn more. On the other hand, you may be feeling a bit overwhelmed by the number of topics we have covered and the number of new worlds and ideas we have introduced. Learning astronomy is a little like learning a new language. At first, it seems there are so many new expressions that you'll never master them all. But with practice, you soon develop facility with them. At this point, you may also feel a bit small and insignificant, dwarfed by the cosmic scales of distance and time. But there is another way to look at what you have learned from our first glimpses of the cosmos. Let us consider the history of the universe from the Big Bang to today and compress it, for easy reference, into a single year. On this scale, the Big Bang happened at the first moment of January 1st. And this moment, when you are reading this chapter, would be the end of the very last second of December 31st. When did other events in the development of the universe happen in this cosmic year? Our solar system formed around September 10th, and the oldest rocks we can date on Earth go back to the third week in September. Where does the origin of human beings fall during the course of this cosmic year? The answer turns out to be the evening of December 31st. The invention of the alphabet doesn't occur until the 50th second of 11:59 p.m. on December 31st, and the beginnings of modern astronomy are a mere fraction of a second before the new year. Seen in a cosmic context, the amount of time we have had to study the stars is minute, and our success in piecing together as much of the story as we have is remarkable. Certainly, our attempts to understand the universe are not complete, as new technologies and new ideas allow us to gather more and better data about the cosmos. Our present picture of astronomy will likely undergo many changes. Still, as you read our current progress report on the exploration of the universe, take a few minutes every once in a while just to savor how much you have already learned. All right, and that is the end of Astronomy Chapter 1.